Okay, so we're going to use some linear algebra in this class. Has anyone had a course in linear algebra? One person? Maybe if you're minoring in math or something, you might take it, right? So so this will be absolutely very, very simple review for you, but for the rest of the class who hasn't had, it's good to know a little bit of linear algebra. It makes a lot of the things we're going to do with respect to stress in this class much easier, okay? So these are concepts that you'd learn in the first week of a linear algebra course, and things that you may have actually picked up in your other courses, like vector matrix multiplication, matrix multiplication, and other things, okay? So the first thing is very simple. If you have a matrix, and a lot of times we'll write just this matrix as a single letter, A. So we might write this matrix equation as a vector C times a matrix A times a vector B, right? Okay. So who knows how to do this multiplication? It's pretty easy, right? You just take, so C1 is the dot product of the vector B with the first row of A. Okay, that gives you C1. Okay. C2 is the dot product of the vector B with the second row of A. And C3 is the vector B dot product, third row of A. Okay. And so that's what I have there. And there. And there. Just written out explicitly. Okay. So again, in words, and sometimes it's easier just to think about these operations in words. Of course, everyone knows how to take a dot product, right? That's like statics. Okay. So in words, the CI entry, so where I is, we'll say 1, 2, 3, the CI entry is the dot product of the ith row of A with B. Okay? And we'll work an example in a second. So matrix multiplication is a little bit more complicated. Who knows how to do this? Okay. So in a matrix multiplication, we take the dot product of the first column of B with the first row of A to get the first entry of C. All right. And then we take the dot product of the second column of B with the first row of A to get C12 entry. And then we take the dot product of the third column of B with the first row of A to get C13. If you can see that yellow, but then to get the C21 entry, take the dot product of the first column of B with the first row of A, and you just continue to do that until you have all the entries. So there is it is written out explicitly. So you have to take that, do that dot product operation to just get one entry in C, and so on. And again, I think this is easiest in, explained in words. So the Cij, where Ij are the subindices of C. So the Cij entry is the dot product of the ith row of A. So if I is 1, that's the first row of A, with the jth column of B. So if J is 1, then that's the first column of B. So everybody okay with that? And so let's work an example. Oh, I didn't. So let's work an example. Let's take the matrix 2, 1, 3, 2, and multiply it by the vector 1, 2. Okay. So what's the first entry of the result? So let's write it out. Remember it's the vector 1, 2, take the dot product with the first row of the matrix, right? So that would be 2 times 1 2 times 1 plus 1 times 2, right? 1 times 2. 1 times 2. Okay, and then the second row dot product with this is 3 times 1 plus 2 times 2. Okay, so then we just, so what's the first entry? And the second? Okay. And so then for an example for matrix-matrix multiplication, we'll take the same matrix, 2, 1, 3, 2, and we'll multiply it by 1, 3, 1, 2. Okay, what's the first entry? It's the first column of B. If this is A and this is B, it's the first column of B dot product with the first row of A. So 2 times 1 plus 1 times 1. Okay. Just put some lines in here so we can keep the entries straight. All right, so the second entry, this entry up here in the upper right corner, is going to be the second column of B with the dot, taking the dot product of the first row of A. So 3 times 2 plus 2 times 1. Right. So then the lower left entry is the first column of B with the second row of A. 3 times 1 plus 2 times 1. And finally, 3 times 3 plus 2 times 2. Right? And then just add them up. 3, 8, 5, 13. Everybody okay with that? By the way, we're all engineers, right? We're not mathematicians, okay? So after you can demonstrate that you can do this once or twice, I have no problem with you using the computer to do this for you, because once you know how to do it, it's just computation after that. And as engineers, we're problem solvers. Right? And we certainly don't want to make a mistake in some silly algebra when the computer can do that flawlessly. It will never make a mistake, right? So after you sort of understand the concepts, I have no problem with you using MATLAB or something to help you do these computations. Okay. So they're just the results of those two examples. I try to, when I'm writing a matrix, I try to use the square brackets, and a vector, I use braces. I'll try to be consistent, just so you know. And a vector is always a column vector. So if I write a vector, if I just say a vector v, understand that its entries are a column vector, right? So then if I were to write v transpose, then that would be a row vector. So you understand what the transpose is? It's just you just literally transpose the rows into columns. Turn a row into a column. Turn a column into a row. All right. So the determinant of a matrix, you guys have probably seen this in some other classes, but if you haven't, it's the determinant of A is just A times D minus B times C. And, instead of trying to memorize that, I just always understand that you're basically, it's like an X. So you're multiplying A and D, and then you're subtracting the multiplication of B and C. So where black is positive and blue means subtract the product. Okay. So the determinant of a 3 by 3, there's the formula for it, but again, it's actually not as complicated as it looks. Basically, you take A and cross out the rest of the entries in the row in the rows and columns, and then you take and you multiply A times the determinant of what's left. So then that's E times I minus F times H, right? So then the subtlety is there's a minus sign here, so they alternate, minus plus. There's a minus sign there, right? So then for the second term, you take B, cross out the other entries, and then take the determinant of what's left. So that would be D times I minus F times G. That's this term. And then for C, you take this, cross out the rows and columns, take the determinant of what's left. So D times H minus I times G. And that's that guy. All right. So the determinant can tell us a lot about a matrix. Most notably, if the determinant is 0, it means that the matrix can't be inverted. So that means when I say inverted, later on we'll try to solve some matrix equations where A is a matrix, X is a vector of unknown things, and B is a right-hand side vector of known things. And the solution to this is A inverse times B, okay? So that's the solution. If the determinant of A is 0, then the inverse doesn't exist, so we can't solve this. So it's sort of a quick way to know if there's an actual solution to this problem, if you know if the determinant's 0. All right. So again, in solving matrix equations, so here's this matrix equation I wrote down just previously. Okay, and here it is above in component form. So when we solve this, all of the entries of A would be known. They'd be numbers, okay? And all of the entries of B would be known. They would also be numbers. And we're looking to solve for the unknown x's. Right? It's just an algebra problem, but it's just written. You know, it's just a system of equations. We just wrote it in matrix form, right? So when we do this, and this is actually the way the computer solves this system of equations, or one way it does, is it uses a very systematic but simple set of rules, okay? And those rules are that swapping rows doesn't change the solution. So if we're solving for x, if I swap the rows, it doesn't change the solution, okay? And think about that. If I wrote this out as a system of equations, if I reordered the system of equations, it wouldn't matter, right? In the solution, okay? So when I swap rows, it doesn't change the solution. If I add rows together, it doesn't change the solution. So I know you've done this before in 8th grade algebra, right? You have two equations. You add one to the other, or subtract one from the other, and to eliminate one of the variables to get a solution, right? So this is nothing more than what we're doing in linear algebra. So if we add the rows together, it doesn't change the solution. And if we multiply a row by a scalar, it doesn't change the solution, okay? So when I said subtract, you could think of the operation of subtracting as multiplying by -1 and adding, right? And so that's what we do, or when the computer solves these large systems of equations, it just systematically applies these rules to achieve the solution, okay? And so it'll do it in a sequence, right? Okay? So here's an example, and the solution is there, but let's go ahead and work it out as to how we'd set this up. And work through some of these row operations. And I'm going to go very slow and explicit at first. So we're going to write the system like this. Okay, and again, the goal is to solve for x1, x2, and x3. All right. So has anyone ever done this before? So the goal is to perform these row operations such that we turn this side, the side on the left side of the dashed line, into the identity matrix, essentially. Right? So the identity matrix would be 1, 1, 1, and the rest zeros. If we do that, then we can read off the solution, and I'll show you how as we go along. Okay, so again, if the goal is to get it in this form, we need to perform row operations to basically turn these off-diagonal entries into zeros, okay? Now, you want ones on the diagonal, so one thing that we could quickly and easily do, because there's already a 1 right here, right? And we want it on the diagonal, so the diagonal would be in the first row, okay? And I told you swapping rows doesn't change the solution, right? So I can swap the first row and the third row, Okay, and so that's what I'll do. And again, I'm going slow and being very specific, explicit here, but I'm going to swap row 1 and row 3. And the result will be 1, 0, 2, 3, 0, 0, 3, minus 6, 2, 3, minus 2, 6. All right. I actually haven't worked the solution out in my notes, so don't let me make a mistake. So we're doing this live. All right. So another thing you can notice that if I said I can multiply a row by a scalar and it doesn't change the solution. So if I multiply the second row by 1/3, then this becomes a 1, right? And then I have a 1 near the diagonal. So if I'm going to do 2 row operations at once here. Or maybe I won't. I'll just go slow. So 1/3 row 2 gives us 1, 0, 2, 3, 0, 0, 1, minus 2, 2, 3, minus 2, 6. Okay? Now you can see if I swap row 2 and 3, then I'll have a 1 on the diagonal again, where I want it. So I'm going to swap rows 2 and 3. And I'll go back over here. So I have 1, 0, 2, 3, 2, 3, minus 2, 6, 0, 0, 1, minus 2. Okay? So what could I do next? I need to eliminate these off-diagonal entries. So I need to eliminate these guys. Somebody give me a suggestion. I mean, yeah, I could add the first row to the second, right? That would do something, right? So if we row 1 plus row 2, that gives me 1, 0, 2, 3, 3, 3, 0, 9, 0, 0, 1, minus 2. Okay? So that helped us a little bit. Now what if we multiply the last row by 2, minus 2. Multiply the last row by minus 2 and add it to the first. Okay? What will that give us? So I'm going to say minus 2 row 3 plus row 1. I'm going to go back over here. So I'll have 1, 0, 0, 7, 3, 3, 0, 9, 0, 0, 1, minus 2. Okay? Now I'm going to divide the second row by 3. So row 3 times 1/3. 1, 0, 0, 7. 1, 1, 0, 3, 0, 0, 1, minus 2. And then one more step. Multiply the first row by minus 1 and add it to the second, right? So minus 1, row 1 plus row 2 is 1, 0, 0, 7, 0, 1, 0, minus 4, 0, 0, 1, minus 2. All right. So what's the solution then? What's the vector x? Seven, 4, minus 2. Or, as we have it here, x1 is equal to 7. x2 is equal to minus 4. x3 is equal to minus 2. All right? So just, yeah.
You can switch to the row, so x1, x2 switch. Well, from the second row, we see 3x2 is negative 6, so x2 should be negative.
Let's see if.
Oh, never mind.
Yeah, I mean, I think if you plug these numbers in there, then it is a solution, right? So anyway, this is actually what your computer does when you ask it to, what MATLAB does when you ask it to do. You can also do other iterative type solves, but if you do a direct solve, this is actually what the computer's doing. It just applies these simple rules in sequence to get the solution. Okay? So the last kind of basic linear algebra thing that we're going to talk about, and this is really the most important one, and we need those other things to be able to solve this problem. And this problem, the so-called eigenvalue problem, is very important in many, many aspects of engineering. Okay? So who's encountered an eigenvalue problem before? I mean, outside of, say, linear algebra class, where you solve them and you don't know why. In linear algebra class, they just teach you the problem and they don't tell you the characteristics or the physics of what these things mean. Okay? So an eigenvalue problem is if you have a matrix A, if there's a vector V that when multiplied by A, you do that vector matrix multiplication, if it turns out to be just a scalar multiple of itself, where the scalar is lambda, then that vector V is called an eigenvector. Okay? And lambda is called an eigenvalue. Right? And these eigenvalues have physical meanings in certain problems, and the one we care about in this class is, well, at least immediately, is with relation to stress. And so the example we're going to hold off on the example, and we'll work an example in the context of stress in solving this problem. Okay? But you can see if the technique we'll use to solve it is, if I just rearrange the equation, right? I haven't done anything, just moved it over. And then I'm going to factor out the vector v. And because it's a matrix equation, when I factor out the vector v, it leaves behind the identity matrix. So the identity matrix, any vector times the identity matrix just gives you a vector. Okay? So identity matrix is just ones on the diagonal. And if you do that vector matrix multiplication, you'll see it just a vector times the identity matrix returns the vector. Okay? So for this equation, and I didn't do anything except to manipulate the equation there, but for this equation to not have a trivial solution for v, so the trivial solution would be that v is just zeros. Okay? So for this not to have a trivial solution for v, then the determinant of a minus lambda I must equal 0. Okay? And so remember, a minus lambda I will give us a matrix. We take the determinant of that matrix, it gives us a scalar, or in this case a scalar equation. It'll be an equation in terms of lambda, and then we'll solve for those lambdas. Okay? The order of the equation is dependent upon the order of the matrix. Right? So if you have a 2 by 2 matrix, there'll be 2 eigenvalues. The order of the characteristic equation, that's the determinant the determinant of a minus lambda I, right? This is called, what results in that is called the characteristic equation of a matrix. Sorry, I don't know, at the bottom of the screen it doesn't seem to be writing very well. Characteristic equation of A. All right. So that'll be a polynomial equation in lambda, and the order of the polynomial will be determined by the size of the matrix. Okay. And so for a 2 by 2, it'll be a quadratic equation. You just use the quadratic formula and solve for it. Okay. For a 3 by 3, it'll be a cubic equation. And you can hopefully factor it nicely and solve for the lambdas. Okay, so those will be the eigenvalues, and then the corresponding v's are the eigenvectors. And again, we'll work an example in the context of stress here in a minute. Okay? So we'll just have to hold on to that. So let's talk briefly about how vectors transform. So if I have a coordinate system x and y, and I rotate that coordinate system by some angle theta, so now I have x prime, y prime. Okay. Let's write down x prime and y prime in terms of x and y. So let's write the new coordinate system in terms of the old one. Okay. So this is just geometry, right? So we're going to say x prime equals what? What is x prime in terms of x and y? Right? It's the projection, right? I want to write the x component first, right? So what's the projection of x prime down onto the x-axis? It's this length, right? And what is that? It's the cosine of theta, right? So it'd be x cosine theta plus, what's this distance? Y sine theta. And then y prime is what? What's this distance? It's the cosine, but it's in the negative x direction, right? So it'd be minus x cosine theta. I'm sorry. That's the sine, right? That's the sine. Sine theta plus y cosine theta. Okay. So now let's just write this in matrix in our matrix notation. So this is just two equations. We can write them like this. X prime y prime is equal to cosine theta sine theta minus sine theta cosine theta times x, y. Okay? So that's just in matrix notation. So this guy is called a transformation matrix, and it's written Q in my equation here. Right? So if we have a vector v in one coordinate system, and we want to know how it transforms into another coordinate system, v prime, it transforms through this transformation matrix Q. Okay? And there it is. So this transformation was a simple rotation in 2 dimensions, right, about the z-axis. Okay? So if I had a third, so in this case it was just x and y, but if I had x, y, z, I'm just rotating about the z-axis, so there would just be a 1. It would just be, so if it was in 3 dimensions, Q would be cosine sine 0 minus sine cosine 0, 0, 0, 1. Right? Because the z and the z prime are the same, right? I just rotate about the z. Yeah. Well, again, right, okay. Okay. So if we have x and y and x prime and y prime, okay, z is poking out of the board, right? So is z prime. They're coincident, right? I rotated about z, so z and z prime are both sticking out of the board in the same direction, okay? So when I write the equations, x prime equals cosine theta, I won't write it all out, cosine theta x plus sine y, y prime equals minus sine x plus cosine y, z prime equals z, right? So then when you put it in matrix form, you get what I wrote out. Okay? So a matrix transforms in this way. Okay? So where Q is the same transformation matrix, it's just now it's applied on both sides. So, by the way, in matrix multiplication, we didn't talk about it. I'll probably give you homework to show that in matrix multiplication, the side you multiply the matrix on matters. You can't just, so in other words, if we look at SQ, right? S is a matrix, Q is a matrix. The result is going to be a matrix. That is not equal to QS. Okay? It's not equal. So the order matters if you multiply on the right or on the left. And so in this case, Q transpose, again, the transpose operation is you're just literally swapping rows and columns. So what would the transpose of Q be? If Q is cosine theta, sine theta minus sine theta, cosine theta, huh? Yeah. So you'd have cosine minus sine, sine, cosine. And again, we'll see how this matrix transformation is important very soon. In fact, if Q is chosen, so when we define Q, we define it in terms of an angle theta, right? If we chose the angle theta just right, such that Q coincides with the eigenvectors, again, we haven't worked an example yet, but we will. So if we choose Q such that it coincides with the eigenvectors of X, it will diagonalize S. Meaning this S prime, if Q is chosen such that you have V1, V2 for a 2 by 2 matrix, right? Where these are vectors. So Q would have entries Q11, Q12, Q21, Q22, right? If they were chosen just right, then when I perform this transformation, what I get, what S prime will be diagonal, meaning it'll have entries only on the diagonal. So you'll have S1, 0, 0, 0, S2, 0, 0, 0, S3. So if we choose it just right, we get that, where those diagonal entries are the eigenvalues. Okay, and again, eigenvalues will be something special. We'll learn something soon in terms of stress. Okay?